sequence of principle of nested ball. Okay. Hence, the principle of nested balls is telling me that there exists an element x, a unique x, in the intersection of all these balls actually. Now here's the question, would that x be in an?
Union of A.
In any of an actually? The answer is no actually. Just think about it. Alright, so let me put it precisely here, shall I get rid of it? Let me put it precisely. Okay. So by principle of nested balls, okay, this sequence of centers xn is going to converge to some x as n goes to infinity. Then obviously this x is going to be in omega. It's not going to be outside omega. Okay? Such that if you take the intersection of all these closed ball, you're gonna get x actually. You're gonna get x. Alright? Now here is this, why x is a very interesting species. Just think about it. So x is in B of x1 R1. But B of x1 R1 is different from, it has empty intersection with A1. So something which is in the first ball cannot be in A1. So x cannot belong to A1 actually. And similarly, this x is also in, x2 R2, the ball of x2 R2.
And which is not in.
And this has an intersection, empty intersection with A2.
A2.
So this x cannot be in A2 actually. Okay? And hence I can show that this x in general cannot be in A3 and hence in any of an for all n belongs to n. So what did you do actually? So what you had? So you found a creepy creature, okay, which is in omega, but not in any of an's actually. Hence, now since I can more formalize it, since Bxn Rn intersection an is empty, so this implies that x, okay, for all n in n, so this implies that x cannot exist in an actually, for all n in n. Now this is a contradiction. This is a contradiction. To fact or assumption. That omega is the union of n belongs to n, an, and this completes the proof. Okay? So what we showed, that if you assume that none of these closed sets contains an open ball, none of these closed sets contain an open ball, this is going to lead you to a contradiction. Hence, the negation of this statement that at least one of these, what do you call, closed set is going to contain an open ball. So therefore, the Baire's theorem is true.
सर मुझे अभी तक एक कन्फ्यूजन हो रही है, जब हम assumption ले रहे हैं स्टार्ट में, उसमें जब हम ये कह रहे हैं कि there is no any subset containing any ball.
There is no, so an, so none of these an's contains open ball. None of these an's are. I'm not talking about any subset of omega not contain.
हाँ ठीक है सर.
None of these an's contain open ball.
तो जहाँ पर जो हम बात कर रहे हैं containing open ball, इसका मतलब कि वो properly उसके अंदर है ही नहीं, out of that. ठीक सर.
ठीक है. So this is what, you know, it's interesting result. Apparently, it's C minus, which has no connection with the real world. Okay, and we're going to see that, you know, it has a connection with many of interesting theorems, which have, you call again, connection with the real world. Okay, so are we happy with the Baire's theorem? So if we are happy with the Baire's theorem, now I'm going to move to the sum of consequences that I talked yesterday of this Baire's theorem. Okay.
वीडियो करे
Okay. So the next and the first consequence that we are interested in of this Baire's theorem is for your so-called uniform boundedness principle. Uniform boundedness principle. Okay. Before stating this result, I'm going to define two kinds of boundedness. First, uniform boundedness of linear operators, and the point-wise boundedness of linear operators, or a collection of linear operators. So what does this principle is telling us? That under certain conditions, okay, this uniform boundedness and the point-wise boundedness are equivalent to each other. This is what that. Let tau be a collection of linear operators. Okay. From normal space E into normal space
F.
So it's a collection of linear operators.
Normally F.
Now this collection of linear operators is called uniformly bounded bounded. Okay. If
distance in terms of
there exists a constant. Okay. Essentially, what does this mean? So we know that what is the meaning of a bounded operator. So we know that the meaning of bounded operator is that, okay, there exists a constant such that the norm of this operator is less than or equal to this constant, or the inequality that you have. Okay? Now, if I change a linear operator, I might have another constant. Some C prime, so on and so forth. Okay. Now, by the uniform boundedness of a collection of linear operator, I mean if there exists a constant in such a way
for
that
every
each element of this collection is bounded by this fixed constant. Okay. Each element of this collection is bounded by. So there is a constant C such that
operator norm
okay. So the operator norm of T is less than or equal to C
for all t and
for
tau.
all T in
Tau.
the collection. Okay? Are you getting the point? And interestingly, it's not a big deal to get such a T. So imagine that you have a collection of
C's.
such C's and you take somehow supremum. But obviously supremum does not always exist. Anyway, ठीक है जी? So that's what it means. So if this is true, so I can make this condition even weaker actually. So this must be also true, that the supremum of these norms of T's of the T's from the tau is less than or equal to C. So if all of these are smaller than or equal to the norm of T, okay, then the supremum of all such norm is also going to be smaller than or equal to C. So you can feed this, you can use this as a definition of uniform boundedness, you can use this as a definition of uniform boundedness of a collection of operators are the key condition that need to be verified in order for a collection to become a uniformly bounded collection of linear operator. Or you can, I can simply say that the supremum of T of all T's in tau and their norms is finite. That's also an equivalent computation. So if I say that this is finite, this means that okay, it must be equal to some constant or less than or equal to some constant. And so these are equivalent conditions. Okay? So what we mean by a collection of operator to be uniformly bounded, it means that I can always find a constant C such that that C is always bigger than or equal to the norm of the all operators in that collection. Okay? And then I'm defining what we call point-wise boundedness. Point-wise boundedness. What is point-wise boundedness? By the way, point-wise boundedness is same as boundedness that we have learned actually. Okay. In other words, a collection tau. Okay, so collection tau is what we call pointwise bounded. Okay? If for all t in the tau there exists a constant c, okay, depending on what t, such that the norm of the f is less than or equal to, okay, c times of norm of f for all f in EF. This is what the pointwise boundedness of.
For all t and tau and for all f and f.
So for all tau there exists a C actually. Okay. We have to be careful. So essentially what we are saying that tau contains, tau is a set of linear bounded maps actually, simple linear bounded maps. But if tau is a collection of linear maps in such a way that such a condition is satisfied, then you're going to call that collection as a uniformly bounded collection of linear operators. There's a really thin difference between both actually. Okay? So here's a point. Which boundedness implies which? What do you think? In general. Any guess? No guess? Uniform implies pointwise. Just think about it. This in general cannot happen. Just think about it. Why? Because for each t you have a c actually, and you collect all these c into a set. Is it necessary that you should always get a supremum? Unless you have an upper bound. But from this we can reduce this. Okay. So actually the uniform boundedness principle is a principle that tells you that under what condition uniform boundedness is equivalent to the pointwise boundedness. That's it. That's what it tells you. Okay. Uniform boundedness implies pointwise boundedness in general. Implies pointwise boundedness. Why this must be the case? Let's think about it. So if I have norm of TF, so there was T is an element from tau actually, from that tau. So this T is an element from the tau which is uniformly bounded actually. It's a collection of uniformly bounded elements. Okay. So what can we do? I can say that this must be same as the norm of T times of F. Okay. And then I can say that this is less than or equal to the supremum of, say for example, norm of S, where S is in tau. In other words, this T is just one element from this tau, while this, that's a supremum of basically what we call times norm of F. But since we have, our assumption, in our assumption that is uniformly bounded, so this must be less than or equal to 3 times of F. Okay. So what does it show? It shows that T is pointwise bounded. Okay. So uniform boundedness implies pointwise boundedness. Okay. I would like to write now the principle this part, or shall I write it here? So I would like to clearly state now what is the meaning of uniform boundedness principle. Okay? So it's pretty simple in its statement. It says that if you assume, so tau is a collection of linear operators from normed space E into the normed space F. Now if you assume that an additional thing on this E, that this E is not only a normed space but it's also a Banach space actually.
Complete.
Okay? Then there is no difference between uniform boundedness and that's what the key principle is, that let E okay, be a Banach space, and tau be the collection of operators from E into F such that it's linear. Okay? Then that will be the collection of bounded linear operators. I think bounded is a mistake. Then tau is what? Tau is uniformly bounded.
If and only.
If and only if tau is
Pointwise
bounded. And by pointwise boundedness, as I mentioned, that each element in tau is bounded in this sense. Okay? In the usual sense. Tau is pointwise bounded. Okay? So that's simply the equivalence of uniform boundedness. And so what you need additional thing is that E must be a Banach space. Alright. So I'm going to prove this by proving a lemma first. Okay? And then we can reduce this result pretty easily. Yeah, another duster. Alright, so I'd like to prove a little lemma. So I'd like to prove a little lemma. Does this work well? Yes, way better. Right? Alright, so see a little lemma, pretty interesting lemma. Then we can write a proof of uniform boundedness principle. Okay. The lemma is this. So let P be a bounded space. And let K be a very interesting subset of EL. Okay? Be a subset. K be a subset such that it has two properties. It's a pretty interesting subset. So the first interesting property that it has is that its K is midpoint convex. Okay? K is midpoint convex. Guess what must be the definition of midpoint convexity? Have a guess. So if you take any two elements from K and take their average, it must be there. So for any F comma G in K, we have F plus G over in K. Okay? It's midpoint convexity. The second is that K is symmetrical. That is, that if we pick an element from K, then its additive inverse must also be K. So if I have a bounded space and a K which is midpoint convex and symmetric in this sense. So these are not two standard definitions. They are shortcut these are just a way to say these two conditions. Then if K contains a ball, okay, that is centered at some F with the radius R, okay, which contains some F with the radius R, then okay, I can somehow kind of translate this ball in such a way that I can translate out this ball. Translation. It's not a what do you call it, Euclidean space, but I'm just giving an intuitive way that I can translate this B from F onto an element which is 0 with the radius R such that it's still contained.
zero element है इसका.
So in other words, if this is my K, okay, and this is a point F, and that's a point 0, okay, and if I draw a ball of a radius R on this, what do you call, point, which is entirely contained in the set K, then somehow I can translate it using the midpoint convexity and symmetry. Somehow I can move it around in such a way that the same ball now centered at origin, okay, and it's still contained in here.
Sir, we are 0.
Okay, so this translation is my intuition, okay? It might not be the translation, but we can see it actually. We can see from the midpoint convexity that somehow we are going to translate. We are going to move around in such a way that.
Where 0 is a 0 element of E, the additive
Yeah,
item.
yeah, yeah,
So means K must be containing the.
yeah.
In other words, K is also vector.
Okay, so why 0 must be